Record. Hello, everyone. Welcome back. Oh my God, look at that 10. Oh my God, you're right. So, everyone, welcome back to another exciting edition of Math 140. We have 4 chapters to go. And then we are done. Oh, you're late. So we're doing fairly well time-wise. If we finish it in 4 days, or maybe even 3, that does give us some time for review at the end of the semester, which is nice. You all know the day of the final is a Saturday, 3 to 5 p.m. Any people who are going to claim religious persecution by having it on Saturday? Anyone? 3 to 5. 31. Probably. Huh? Saturday? 14th, is it? May 14th. The good thing about May 14th, about having it so soon, is that you get it over with. And then you don't have to worry about statistics for the rest of the week. Yes. There are makeup days if you have a justifiable reason why you can't make it. Here are valid reasons. You're dead. You have multiple finals on the same day. No. Okay, fine. You have COVID or some other sickness that would impair your ability to do the test well. No. What was that? You said you had work? Yes, if you have work and your work schedule has you working on Saturday at that time, that would be a justifiable reason. You're going to your best friend's wedding in Alabama. Something like that. So let's begin. Any questions? Hi. Hey. Okay, let me first update them. They're technically here since we didn't begin. Okay. All right. So today we start another chapter, chapter 21. But before we do so, are there any questions on anything so far? Yes.
What's the chapter 19?
Well, the chapter 19 homework should be due pretty much. I mean, it should be due by now because we certainly finished 19 at least 2 weeks ago. But because I never specifically said when it's due, I will have it due on Thursday. And I will have 20 due a week from today, Tuesday. Because you've had a lot of time for both of them. And normally I mean, 20 would have been due this Thursday, a week from when we finished it. But I'll give you to Tuesday. And then when we finish 21 today, assuming we do so, that'll be due on Thursday. So Thursday, Tuesday, Thursday. Yes.
Can you update the settings for 2021?
Sure. What settings would you like me to update? Free points for everyone? What exactly do you want here? So hold on. We're sorry there's a technical issue with this page. Oh, that's not good. Oh, let's take a look. 19. Oh, Anna, you made it. So 19, what did I say? 19 is due on Thursday. That's the 28th. I just reset 19 to the 28th. And okay, and now let's go to 20. And 20 is due a week from today. That would be May 3rd. And I'm setting it to unlimited, and here's all the answers. So you can't get it wrong, lose points, okay? And then if I go to 21, which is what we're doing today, assuming we finish it, which we should, because, well, we should, that will be due May 12th. And even if I don't finish it today, it'll be due May 12th, because it'll be a week from when we finish it, so. Okay, that's all set. You're happy now?
The specific.
De nada. Пожалуйста.
О, ти вже знаєш, як говорити?
What the, that's not even a word. Okay, so chapter 21, comparing two means. Chapter 21. Can everyone read this? Chapter 21, comparing two means. So if we think about what we've done so far, black one too. Okay. If we think about what we've done so far, we've dealt with one proportion, and then we followed it up by dealing with two proportions. And then we switched over to means, and we dealt with one mean. And then we had the last part of the chapter was comparing two means. But if you think about it, the matched pair t-test took two means, but made one mean out of them by looking at the difference between them. And this chapter is about comparing two means. And like the previous ones, we're going to be dealing with two different approaches: hypothesis testing and confidence intervals. Yes? Your hand's up. Your hand is up. What? It's good, thanks. How was yours? So, comparing two means. Ah, sucks. Yes, it is.
Oh, maybe.
Comparing two, what was it? Comparing two means. So, what if you're interested? You're curious whether or not wait a, just get right in there. It's okay. You're curious whether or not the average American male is taller than the average American female. Maybe you're interested in whether or not the average first grader has a better reading ability than the average second grader. There's many situations where you might have two different populations, and you're curious about a comparison of the average of the first population to the average of the second population. So what do you think is the appropriate method for determining whether or not there's a difference between two populations? What's the first thing you would do? Okay, I'm looking at them. Got it. What do I do with that information?
Create an interval.
What? How do you create an interval? To create an interval, what's the first thing you would do? Before that, take samples. Right? Before you do anything, you take samples. Well, okay, let's take 100 first graders. Let's take 100 second graders. So you take two samples. So the first thing we're going to do before we do anything else is we look at our two populations. And we take two samples. Now, those samples that we take have to be SRSs. So we take two samples, two SRSs, one from each population.
Are there any exceptions for that rule?
No. We take two SRSs, one from each population. They have to be SRSs like every other confidence interval and hypothesis test that we've dealt with this entire semester. They must be SRSs. In addition, the underlying distributions need to be what? somewhat normal, must be normal, or at least very close to it. Very good. And then like the single mean, we're going to divide up our formulas into two different cases. What are the two cases? Well, how do we divide up our study of the single mean problem from last chapter? Whether you know sigma or you don't know sigma. So here, it's a little more complicated because there's two populations. What if you know sigma in one but not the other? We're not going to deal with that this semester at all. For us, there's three cases. Case one, we know sigma 1 and sigma 2. This is case number 1. We know both sigmas. In that case, what test do I use? We use Z. Either the Z interval for two means or the Z test for two means. If you look on your calculator for the tests and intervals, you should see the two sample Z test and the two sample Z interval. When do we use them? When we know both sigmas. 2 and 3 are we don't know sigma 1 or sigma 2. The second and third possibility, we do not know sigma 1 or sigma 2. If you look, and if we do that, which one are we going to use in that case? We're going to use T. Now, if you go to your calculator right now, and you actually look at the two sample T test or the two sample Z T interval, there's something at the bottom. One of the last things that you must choose when you're, yes, the two sample T test. Good, right, excellent. So when you're in that one and you look at all the things that you must fill out, I got to give it this, I got to give it that, I got to pick this, I got to pick that. There's something at the end. Pool. Do we pool it or not? Well, that's going to be our 2 and 3 situations.
What does it mean if it's?
I'm about to explain that right here. So if we don't know them, but we know somehow that they are equal, if we don't know them, but we do know that they are equal, then we pool them together. Otherwise, what do? We don't pull them together. So if nowhere in the problem is there any indication that we somehow know that sigma 1 and sigma 2 are equal, if that does not appear anywhere in the problem, then do not pool them. Whereas on the other hand, if the problem specifically tells you, hey, we might not know what they are, but somehow we know that they're equal, then you do pool them. I'm pretty sure, not 100%, but I'm pretty sure that in this class, we always pick this one. But I don't want to promise that because you might come across a question where they do want you to pull them, huh? You're quick, man. I mean, I'm not sure how you got that so quickly. Oh, wait, maybe it was what I said. Do this one always.
No, it's on the board.
Yes, I know. Thank you for your inputs. Your speaking privileges have not been revoked for the rest of the semester. So, does that make sense so far? Of course, I haven't given you any formulas yet, but let's go to our calculator. Let's look at the two sample, please. Let's look at the two sample Z test first. What does our calculator say we need for the two sample Z test? sigma 1, sigma 2.
List one, list.
Well, wait, list 1 and list 2 is if you have your data, correct? Go to your stats instead.
Bar one,
X bar one.
X bar 1, X bar 2, N1, N2, wait, and a confidence level. Wait, this for the interval or for the test?
This is for the test.
I think the test first.
I said test first.
Yeah, that's what I saw. It's two sample Z test, right?
2 sample Z-test.
It doesn't answer. Yeah, and then.
Okay, right, there's no confidence in it, it makes no sense.
Then you have.
The interval should have it, but not the regular one, huh? So you need sigma 1, sigma 2, X1 bar, X2 bar, N1, N2.
And then you have that, I don't know.
One and it's not equal to, less than, great.
And then, of course, you have your 3 possibilities for the null hypothesis. Remember, you're comparing the 2 means, correct? So if I say, oh, here are my 2 means, the null hypothesis is always equals throughout the whole semester. The null hypothesis has always been equals. So what do you think the null hypothesis is going to be for the 2 sample Z or T test? What is equal? Mu1 equals mu2. The mean for the first population equals to the mean for the second population. So the null hypothesis for both will be that mu1 is equal to mu2. Are these 2 means the same? What are my 3 possible alternatives? Greater than, less than, not equal to. And depending on which one it is, and you have to get that from the context of the problem, that's the one you pick on your calculator before finishing the test. All right, so your 3 alternatives, sorry, mu1 is not equal to mu2, sorry, mu1 is less than mu2, or sorry, mu1 should be greater than mu2. If you look at the 2 sample T test instead of the Z test, there's really only one change. Or technically 2, I guess. But what's the 1 conceptual but 2 practical changes that we make when using the T instead of the Z? Well, yes, if it's pooled. We don't know sigma, so we can't plug it in. Right? We don't have sigma 1, we don't have sigma 2. How are you going to put them in if we don't know them? So what do we use instead? SX1 and SX2. Instead of the sample standard deviation for the first and the sample standard deviation for the second. Yes.
Oh, so just to reiterate, so if we don't have the standard deviation of the population, we use standard deviation of the sample.
Well, if you have the standard deviation of the population, you use Z. If you don't, you're using T. So by the very fact that you're at that section of the calculator, the T test, you can't know them. Because if you did, you should be at the Z test.
Okay.
Right?
So T is for when you don't know.
T is for when you don't know, as it has been for the last chapter as well.
Right.
Yes.
And T is the one that has the pool. Z didn't have the pool.
Well, there's no need to pool the Z because either they're equal and you know that, or they're not equal and you know that, because for the Z, you know sigma 1 and sigma 2. The whole nature of pooling is I don't know them, but they're the same, so let's lump all these things together. With a Z, you know them. So if they are the same, the calculator will handle it. And if they're not the same, the calculator will handle it. You don't have to do that on your own. You only got to do that for the T. Okay? Now, for the T, if you're going to do it manually, there's one more thing that we need. What do we need for the T, for the mean, if we did it by hand? If I go to the tables in the back of the book, and I look at the T table, and I have all my data here, I had numbers at the top, and I had numbers in the left. What were those numbers in each section?
That the probability, the confidence.
No confidence intervals, this is tests.
But for the T.
For the T.
It was showing the 0.5 to 0.5.
Okay, so probabilities up top, 0.05, 0.01, whatever they are. And what were on the left? Not sample size, not technically sample size. It was close to that. But it was not sample size. Well, N is the sample size. But it wasn't sample size. I'll give you a hint. It's some of your grades.
Numbers. We didn't do F yet.
Well, F is part of it. And the other half is D's. DF, degrees of freedom. Remember that, degrees of freedom?
How's it close to?
We're not familiar with these answers.
Well, I've seen your grades, I'm not sure that's true, but still. So, yes,
How's that close to sample?
how's it close to what?
You said, so they said,
Because in the case of the t-test, the degrees of freedom was sample size -1. So it wasn't sample size, it was sample size -1. But now we have a problem. The problem is that we have 2 samples. And they could be of different sizes. So what do we do?
standardized.
No,
Is it out of the polling?
huh?
Is it out of the polling?
No, unfortunately not. Yes,
Can't you just get 2 different scores or whatever it is?
yes, but that's not correct. So,
Average means.
so in the case of 2 samples, there are 2 ways of computing the degrees of freedom. One is really complicated mathematically. The formula is actually in the book somewhere. I don't have it by heart because I never use it. But I'll write it down because your calculator uses it. And it is S1 squared over N1 plus S2 squared over N2 squared all over 1 over N1 minus 1 times S1 squared over N1 squared plus 1 over N2 minus 1 S2 squared over N2 squared.
Do you need this?
Yes, everything I give you you need.
Oh, we were gonna have to do this by hand.
Huh?
Oh, we were gonna have to do that by hand.
No. Who was that who just left? Anyone know his name? Mark, okay. Mark is absent for today.
If he comes back, then.
Then I'll go back and fix it. But he took his bag with him, so. So this is the technical formula for the number of degrees of freedom. It is complicated, but it's what your calculator uses to get the exact value for the degrees of freedom. Notice, by the way, using this formula, unless you're extremely lucky or unlucky as the case may be, this is not going to be a whole number. The chances of this being a whole number are very, very small. So you get a decimal for the degrees of freedom. And therefore, as such, this notion of the degrees of freedom is kind of complicated. As far as we're concerned, it's just a numerical value that is used in the formula. But if you will instead do it by hand, then we use a much simpler formula. And that is, you take the minimum of the 2 sample sizes, whichever one is smaller, and you subtract 1. So if you don't want to use the convoluted formula, and you're doing it by hand, you look at the 2 sample sizes, take the smaller one, and you subtract 1. We call that the conservative approach. So on homeworks, you will see, or even on test, you will see this notion of using the conservative approach. How many degrees of freedom are there for this situation? And all you do then is take the smaller of the 2 sample sizes and you subtract 1. We call it conservative because this number will always be smaller than this number. And a smaller degrees of freedom means that you are higher up on your charts. You're at a higher row. And if you're in a higher row, your confidence intervals are wider and your t-tests are more difficult to reject the null hypothesis. In both cases, we're erring on the side of caution by having a higher number in my chart. That's why it's called the conservative approach. Question?
Are we gonna get to use an example? Are you gonna have an example later that's gonna use the conservative method?
Okay, sure.
Okay.
Questions so far? No questions so far. By the way, we've moved. By the way, we mentioned earlier that the distribution should be normal. And I think it was Frank who said approximately normal, right? Okay, someone else did over here, Alice, approximately normal. If it's not normal, but it's approximately normal, then what size samples do you need to be able to use all these formulas? So it was 30 for the central limit theorem, correct? But we didn't use 30 last chapter. We used 15 for moderate skewness. And we use how much for heavy skewness? 40. It's the same thing here. And on page 465, it says, if the sum of the two samples is 15, if the sum of the two samples of N1 plus N2 is at least 15, then we can use this if there's light skewness. And if the sum of the sample sizes is at least 40, we can use it if there's heavy skewness. Remember, the t-test is rho bust. This is the last thing we did last time. Do you guys remember robust? What does robust mean again? What does robust mean?
If the value of confidence level doesn't change much.
I didn't hear that at all, thank God. What? Say again.
If the p-value of the confidence level doesn't change much when the continues for the use of the t-value are violated.
Conditions. When the conditions for the use of the t-test are violated. So we want it to be normal. Oh no, they're not normal, but it's okay. If it's light skewness and the sample size is summed to 15, go ahead and use it anyways, because the t-test is robust. If it's heavy skewness, but the sample size is at least 40, go ahead, use it anyways, because the t-test is robust. So let's do an example. Oh crap. I don't like this one, but we'll do it anyways. Daily activity and obesity. Huh? Yeah, I know. Okay, people gain weight when they take in more energy from food than they expend. Do we agree with this? It's a common belief that people gain weight when they take in more energy from food than they expend. I'm not a 100% believer in this because this notion assumes that energy in and energy out are independent. And therefore what you eat, like for example, if I eat 100 calories of salad versus 100 calories of chocolate or something like that, this notion of 100 in and then whatever you expend doesn't take into account the type of food that I took in. Because they're not taking into account that, oh, you ate this and then your metabolism will do this and you'll burn more calories doing this. And they're not really necessarily independent, but it's a common held belief. And it's a good starting point for people who are thinking about dieting. Anyways, James Levine and his collaborators at the Mayo Clinic investigated the link between obesity and energy spent on daily activity. So we are examining the link between obesity and energy spent on daily activities. Choose 20 healthy volunteers who do not exercise. Choose 10 who are lean and 10 who are mildly obese, but still healthy, like me. Anyways. Attach sensors that monitor the subject's every move for 10 days. And then we have this data. I'm not going to write all the data, but essentially we have the group. There's the lean people. And then there's the obese people. So we have two groups. We measured the time spent standing or walking, time, the time spent sitting, and the time spent lying down. So these monitors monitored the time spent for each individual, how much time they spent standing and walking, how much time they spent sitting, and how much time they spent lying down. And the question is, do lean and obese people differ in the amount of time they spend standing, walking? That's the question that we're trying to determine. Is there a significant difference between the time spent standing, walking for lean people and the time spent standing, walking for obese people? So if we call group 1 the lean people and group 2 the obese people, then what do you think is the appropriate null hypothesis and alternative hypothesis for this problem? So the null hypothesis says that they're equal, that mu1 is equal to mu2. And what do you think is the appropriate alternative for our study?
V1 is less than V2.
So you're saying that lean people spend less time standing, walking than obese people. I think your alternative would be that, you know, why they're lean and not obese? Because they move around more, right? So we're trying to test whether or not mu1 is greater than mu2. And we have the following data. We have N1 is equal to 10, N2 is equal to 10. We have X1 bar, the first mean is equal to 525.751. X2 bar, the second mean, is equal to 373.269. SX1 is equal to 107.121. And SX2 is equal to 67.498. And the question is, based upon the data that we have, do we reject the null hypothesis and say, yeah, the data seems to indicate that lean people do in fact move around more than obese people? Or do we not reject the null hypothesis? You tell me, what kind of test is this? It will be the 2 sample t-test because we do not know sigmas. So the 2 sample t-tests, I'm going to use my stats, not my data. No, sigma is the population standard deviation. S of x is a sample standard deviation, which we use when we don't know sigma. So X1 bar, 525.751. SX1, 107.121. N1, 10. X2 bar, 373.269. SX2, 67.498. N2, 10. Our alternative is greater than. Are we pooling here? No, there's no indication that we should be pooling here. So we're not going to. In fact, even though we don't do it in this class, there are ways of taking your sample standard deviations and testing whether or not they support sigma 1 being equal to sigma 2 or not. Well, we're not doing it. It's called an F, it's an F test. It's another type of test. We're not doing it. So in our case, we're just not going to pull them straight up. Привет. Отлично. Пожалуйста. What? What do you say? Confidence level? What the hell's wrong with you?
Yeah.
Jeez.
Let me ask you.
I think you're in the wrong one, dude.
No, because you said 2 sample t-test.
Yes, 2 sample t-test. That's correct.
Yes, sir.
Not 2 sample t-interval, but 2 sample t-test.
Cool.
You were saying? Sorry? What was that?
T-test, right?
Yeah.
Yeah, see?
See what?
Is the alligator weight?
Yes, the alligator, yeah? What about the alligator? Yeah. So what's our p-value?
8.411.
It's 0.
It's 0. again, for the 19th time, p-values are probabilities. You can't have a probability greater than 1. So when you see 8.4, you have to say, well, this can't be right. Let me get to the end of the line and see that e negative 4 to indicate that it's 0.00084, and whatever. Which means, what is our conclusion? Yes. Oh, I'll take a look. Meanwhile, what's our conclusion? We reject the null hypothesis. The data certainly seems to indicate that non-fat people. So our p-value is low, the null must go, and lean people seem to move around more. Now, if you look at this page, how many degrees of freedom are there?
19.
Not the conservative approach, the calculator approach. What? It literally says DF equals 15 point something, 15.2,
Wait, where do you get the DF equals?
where it says DF equals.
17.35? Whoa.
What?
17.35.
Your shit's all wrong, man.
It literally has the same, like.
I think your shit's all wrong, dude.
No, but for D it says 8.4.
I think you might have put the data in incorrectly.
No, I haven't.
Oh yeah, can you read me the numbers that you have written down?
All right, so X1.
Yeah.
525.7.
So again, was it?
525.751.
Okay,
X2, 373.269.
okay,
107.121.
yeah,
67.4948.
yeah. And what are your ends?
1010.
What the hell? And you pooled or not pooled? Did you pool?
Wait, what?
Did you pool?
The
The bottom, did you pool?
One is less. Oh, yeah, I said no. Cause I.
No, he put mu1 is less than mu2.
You did less than? That wouldn't make a difference for degrees of freedom though.
So 15.17350391.
Yes. Yeah.
Oh,
Yeah.
yes, yes,
See, how you tell me no when it's right?
because you said something else, didn't you?
No, I said 15.73.
No,
I said no.
You said something else, dude.
No, I did.
Your shit was wrong.
Check the clips.
So, anywho, does that make sense? What?
Isn't degrees of freedom, you said like n minus 1, right?
It was for one sample. This is 2 samples. It's a different formula.
Oh, so, okay.
Now, if on the other hand, I didn't have my calculator, and I didn't want to use that formula that was on the board, and I wanted to use the conservative approach,
Yes.
how many degrees of freedom would I have? 9, which is less than 15.
How'd you get 9?
10 minus 1.
Oh.
Now, my calculator can't do that for me. I'd have to do it by hand. I'd have to either go to an online calculator where I get to plug in degrees of freedom, or take a table from the back of the book and say, okay, degrees of freedom 9, and then read across the table and hope I get a number that's close. Yes,
But they said we can't do n minus 1 with 2 means. So why would you do n minus?
because you do the minimum of them minus 1. And if they're both 10, 10's the minimum. Yeah. Does that make sense? Any questions for this approach? Of course, your calculator is computing your t-score, so we should know how to get that. So what is your t-score for your 2 sample test? Well, it's your data minus the assumed mean over the standard deviation. That's always your z or your t-scores. So what is your data here? If the null hypothesis is claiming, if we're testing to see whether or not the means are equal, then what is the closest numerical value that we can possibly get from our data to the true value of the difference between the two means. Right? mu1 minus mu2. We're curious, how far off are these? What's the closest value we can use for the difference between mu1 and mu2? X bar 1, x1 bar minus x2 bar. This is the closest we can get to the true difference. And then we subtract the difference of the two means according to the null hypothesis. And what is the difference of the two means according to the null hypothesis? What's the difference of the two means if the null hypothesis is correct? 0. Now, in a more complicated class, you might not be trying to show whether or not the mu's are equal. Maybe you just believe that males are on average 3 inches taller than females, in which case you're testing whether or not mu1 minus mu2 is 3. But in our class, it'll always be 0. And then the question is, what do we divide by? What is the standard deviation for the two samples? That's not N1 plus N2, you're not taking into account the standard deviations at all. So, yeah, what is it? No. So in the one sample case, we did S squared over N, and we square rooted them. Here, we take one for each, add them, and then we square root it. That's it. That's the t-square. Now, if I wanted to calculate the p-value, I would just calculate the probability of being past this, more extreme. Your calculator does it for you. It gives you the t-value, and it also gives you the p-value. And at the end of the day, what is the one and only number you need to make your determination? The p-value. Nothing else matters.
Zero?
Huh?
Is it x1 minus x2 minus 0?
Yeah. This is the mean if the null hypothesis is true. Now, for the same situation, let's go ahead and calculate a confidence interval for the difference of means. Where would I go to in my calculator to calculate the confidence interval? Two sample t interval. So let's go to the two sample t interval
We're going to T instead of C
because we don't know sigmas.
$95.
95. So we go directly to the calculator. 67.2, let's say, just 3 digits. I'm running out of room. 200, yeah, it's 230. So,
You want to round it or just like?
3 digits is fine. So, what do we conclude based upon this confidence interval? If I said, interpret this confidence interval in the context of the problem, what would you say? Hand up, airing the pit, or what are you doing? Okay. So how would you interpret this confidence interval in the context of the problem?
The data supports that 95%.
You're doing good in the data supports, yes.
You're 95% confident that green people, they stand and walk this much more than between you there.
You're not really using the interval at all. I mean, again, you said something good. That's something good, but not complete, yes.
95% sure that lean people will, I think it's Khaled.
Time, this is time.
They stand or walk around and do whatever it is between 62, 67.2 and 238, whatever units they are.
Seconds, let's say, minutes, maybe, I don't know. Again, missing one thing is still not complete. Still not complete for full credit. Closer, keep getting closer every time. So we are 95% confident that the true difference between how many seconds lean people walk and obese people walk is between this number and that number. Probably minutes, probably not seconds, probably minutes. Because if it's 1 minute more, you're probably not going to lose that many more calories. So probably minutes. We are 95% confident that the true difference in means between the number of minutes that lean people walk and that obese people walk is somewhere between this number and that number. The key word is that the true value. If you just say it's somewhere, the difference is somewhere between these, difference of what? It's that unknown true value that we're trying to pin down. Most importantly, what number is not in this confidence interval?
The mean of,
No. 0. Because that's what the null hypothesis claimed was the difference. The null hypothesis claimed the difference was 0. And 0 is not in here. How are you going to stand there, look me in the eye, and tell me that the true difference is 0 if 0 is not in your confidence interval? No, sorry, I am rejecting that notion. And it appears, at least the data supports the fact, that lean people do in fact move around more than obese people. Now, I don't know about you, I move around all the time. Because, I'm teaching. I don't sit when I teach. I mean, it's lazy to sit when you teach. You got to walk around a lot. Huh? Yes. But I lose count at about 3 or 4. So- Huh? Oh, yeah, it does tell me. Yeah, I had the 10,000 thing. What's it called? A Fitbit? Right, I have that on here. I just don't know how it works.
Yeah, you're funny to talk about it.
Well, when I play tennis, I don't have it in my pocket. Who are these people calling me? Why am I so popular? Anyways, anyone have a question for anything so far? Yes, no, maybe so? Pretty easy, right? Well, that's the idea. Yes.
The difference between the HO and HA is the HO is what your hypothesis is.
Not exactly. Usually the HA is what your hypothesis is. When I go to Subway and I say, Subway, I've measured all my sandwiches that I've gotten over the years. And the average of those sandwiches is 11.38 inches. So I'm going to hypothesize that you've been lying to us all these years, and that really the true length is less than 12 inches. So my alternative is that it's less than 12. But what am I fighting against? What am I trying to change? What is the status quo? If I'm wrong, what's correct? That it actually is 12. That's the null hypothesis. So the alternative or the research hypothesis is what I'm trying to establish from my data. Because if I believe the null hypothesis, why would I test it? All right, you test something that you believe to be false or that you believe is changed. You don't test something that you believe is true.
So the null is what is generally.
The null is what is generally acknowledged, or the status quo hypothesis. The alternative is what you're thinking might be the real scenario. Another way to think about it is the equal sign always goes with the null hypothesis. Always. So if I say I believe something is less than 5, the null would be equal to 5 and my alternative is less than 5. In chapter 24, we will have some other alternatives And they will not involve equal signs at all. So that statement of always having the equal sign is true for the Z and for the T. But it's not true for the chi-square, which will be our last scenario. Yes,
Just the T says right there, do we, since the calculator gives us a, and we create the calculator, do we just go by this one or do we do that?
well, if the problem says, well, if the problem says calculate the T-score, the calculator gives you that as well, right? So really, I mean, I give you this for completion's sake, but the calculator really gives you everything you need. Okay? What is the formula for the confidence interval, by the way? What's the generic formula for the confidence interval?
Sigma over.
Not even close. We don't know sigma.
Standard deviation over square root of n.
So, would anyone else like to give it a shot?
What was the shot? What was your question?
What's the formula for the two sample?
Confidence interval?
Yes.
Alright, watch. CI.
No. Oh, okay, go ahead.
T.
No.
Plus.
No.
minus,
Well, there is a plus or minus. I'll give you that. There is a plus or minus.
Z.
Which one?
Z.
Z
Star.
star, but unfortunately,
T.
Was it?
Twiddle or not?
T star, not twiddle.
Square root. Yes, sir.
He had divided by sign.
Put X more, 1 minus X.
X.
S. S of X. Oh, wait, no, T, so you know, sigma. Wait, no, T, you know.
You don't
S
have
of
the
X.
next one.
one. Squared.
Plus
Plus. S of X. 2. Squared. Over. And 2. S of X, the first one's over N 1, right? Yeah. Over.
Multiplying by 1 minus.
It looks right.
Same as that. You know, it was like kind of like on the board the whole time. It's like you're psychotic. Any questions with the two sample T test? Let's do a few problems because we're done with the chapter. So. Let's see what you got. What the hell was that? What the? Hell? You guys are, for those of you watching this video on a later time, I apologize. All right. A question for you. In the 2009, just listen, you don't have to write anything. In the 2009 NAEP sample of Texas 8th graders, whatever that is, some test. The mean math score was 286 for female students and 287 for male students. To see if this difference is significant, would you use a 2-sample t-test, a matched pair t-test, or a 1-sample t-test? Final answer?
Yeah.
Would you like to phone a friend? Oh, you don't have many. Okay, so it is correct. What was that? That doesn't count. So they're all in Russia. So the answer is yes, it's a 2-sample t-test for a couple of reasons. One, You wouldn't use the one sample t-test because we have two samples, males and females. Second, how would you pair them up? One male to one female, it's not really a pairing. The numbers are the same, but there's no reason why there should be any association between the male and the female in that pairing. So essentially you have the male group, you have the female group, and you're comparing them. That is the very nature of a two sample t-test. Yes?
Is there any way you could change it in this situation where it would be a match pair test? Like, how can you make it so that is a
Brother sister pairs, maybe? Have a brothers, twins, see if there's a difference between twins.
that'll make
So brother and sister could be a matched pair.
quality?
Nurture, nature, they're the same upbringing, I don't know, something like that.
So it's variables that we don't have control over, like we can't really predict.
No, I'm just pairing them,
Uh,
right? A brother and sister twin pair would have some kind of association between them that might be relevant. So I'll pair them up and see if there's a difference between the male and female of each pair, rather than generic males and females. That might be a way I would do a matched pair test. All right, let's do another one. Oh, it's hard to sometimes find questions. You know what? One second. I have the. Math 140 workbook. We haven't really used that much this year. So let's see what I have here. Inference for a population mean. That was the last chapter, correct? So this is, yeah, this one here is inference for comparing two means. Here we go. Okay. Here we go. If at any time you want me to stop and write something down because you feel it's relevant, go right ahead. Researchers randomly assigned participants either a tall, thin wine glass called a highball or a short, wide wine glass called a tumbler, each of which held 355 milliliters. Okay. Well, I don't know what it is yet. I just have some people having the tall, thin one, some people having the short, wide one, but they both hold the same amount, 355 milliliters. Participants were asked to pour 1.5 ounces, a shot of liquor into their glass. Did the shape of the glass make a difference in how much liquor they poured? Both groups had 99 participants. Okay, so. N1 and N2 are both 99. The average, the mean for the tall glass was 42.2 milliliters. All right. 42.2 milliliters. 42, you better write it down. 42.2 milliliters. That's your mean. That's your X bar. That's your sample mean. What? X, well, if it's the first group, if you're calling the tall, thin glass your first group, then it's 1. If you're calling the other one the first, then it's 2. It's your choice.
So 42.
0.2 milliliters. Whereas the mean for the tumbler group was 47.9 milliliters.
So
Oh my God, 42.2 and 47.9.
So X bar is the mean for this sample, and X is just the mean for the population.
What the hell's X?
Mean,
No, mu, yes, but we don't know mu.
all right.
If I knew mu, I wouldn't need to take a sample. The sample standard deviation for the tall thin glass was 16.2 milliliters. 16.2,
What is that? That's 6.1? 62.2?
16.2. And the sample standard deviation for the short white glass was 17.9 milliliters. Construct a 90% confidence interval for the difference. You can't. 90%. Construct a 90% confidence interval for the difference. So what happened with N? Got it. What? Construct a 90% confidence interval.
Like 0.9.
Yeah, that's what you said.
No, he said 9%, 0.9. Wait, so we only know X bar?
We only know, I gave you N's, X bars, S X's. No, you made a mistake somewhere. Or maybe I made a mistake somewhere. No, I think you made a mistake somewhere. 9, they're both 99. Both sample sizes are 99. Whoopsie. What do you get? No cool, no pool. They didn't give me any in the, huh? Well, what's a DF? Okay, what's your confidence interval? Yeah. The confidence interval should be some number to some.
Okay, so negative 5.975.
I got negative 9.71 as well. I did. I didn't say no. I got in my head, huh? This is a confidence interval, not a test. Yes,
What's the confidence level?
90% confidence.
Could you explain again? He said 9%.
Why would I ever say 9%?
9%.
Why would I ever say 9%? When have we ever used 9%?
You said 9%. 0.9% is like less than 1%.
Yes, question?
No, you said 9%.
I said 90%. Okay, raise your hand if you heard 90. Yes, question?
Could you explain why, whether it's before or not?
Did they tell you to pull? That's why it's not pull.
So this is almost like now.
They would have to.
Okay. So what time?
It's not a test. We constructed a confidence interval. 2 sample T interval. Yes.
So what's the definition of sigma?
Sigma is the population standard deviation. Well, we don't know sigma. So the best we can do is use the sample standard deviation instead. I don't have it. They didn't give it to me in the problem. Yes, but I don't have the population one.
So we use the standard deviation of the sample.
Yes.
Sigma for the population is what we really.
No, I don't care about it. I mean, if I had it, I can get a more accurate result, but I don't need it. Yes.
How would you explain the interval?
You mean what, in the context of the problem? Hold on. 42.2. There you go, sweetie. Thank you. Honey bunny. So the true difference between the amount of liquor poured in using the tall thin glass compared to the short white glass We are 90% confident. It is between negative 9.71 milliliters and negative 1.69 milliliters. Either way, what number is not in that confidence interval? 0, which means the data certainly supports the fact that the tumbler gets more liquor than the tall glass.
So was this whole experiment with they had an eyeball to pour?
Yes.
Oh,
So from the eyeball perspective, people are more likely to overshoot the mark if they use a short wide glass than a tall thin glass.
what did the negative intervals indicate versus the following interval?
Well, your first one minus the second one, if you did second minus the first, the numbers will be reversed. It'll be positive or negative, depending on which one you do first. So for us, because it's negative, that means the first one is smaller than the second
Oh, so they poured less in the.
in the tall one. Correct. Yes,
That's what I was asking, wondering that.
that seems to be the conclusion of the data. Make sense? Are we done? Are we done? Are we done?
Another one.
I'm looking for questions here. There's not many, actually. All right, here's another one. This is very similar to a test question because it's got like A, B, C, D, E to it. So you're going to see in the final, some of your short answer questions are going to be like this. Here we go. Listen very carefully so that you don't mishear any of my numbers. A mathematics test was given to a random sample of 1,000 17-year-old students in 2004.
So is that N for both? Like, just another-
What's both? We're so far in the problem, do we have a both? Hold on. A mathematics test was given to a random sample of 1,000 17-year-old students in 2004. What's the both? Not yet, at least.
Yeah.
And again, to another random sample of 1,000 students in 2014. And 1 equals 1,000 and 2 equals 1,000. The mean score in 2004 was 300.4. X bar 1 equals 300.4. In 2014, 300.4.
300.
The first one, the mean score in 2004 was 300.4. In 2014, it was 305.4. Is this 5-point change evidence of a real difference? Or is it plausibly just due to chance? Part A, state the null and alternative hypotheses. Part A, state the null and alternative hypotheses. Yes,
So the null was you said it was by chance, right?
I didn't say anything. I'm asking you, what is the null and alternative hypotheses? Yes, what is that they are equal?
Two different samples. Mu1 and mu1 is equal to.
What says that mu1 is equal to mu2? The null hypothesis claims that mu1 is equal to mu2. What is the alternative hypothesis?
Mu1 is not equal to.
So the question says again, is this 5-point change evidence of a real difference in means for the 2 years, or is it plausibly just due to chance variation? Nowhere in the question does it seem to indicate that we're curious if the scores went up, but rather if there was a difference. As such, what should the alternative be? Not equal to. Be more specific, give me the whole thing. HA colon is? Mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0, either one of those. Part B. The sample standard deviations were 34.9 for 2004, 34.9 for 2004, and 30.1 for 2014. Again, the sample standard deviations were 34.9 for the year 2004 and 30.1 for the year 2014. Compute the test statistic.
That's the best, right?
No. S sub X is the sample standard deviations, which they gave you.
What do you mean for this?
Compute the test statistic. Did they say to pool them?
So you want the T?
I want the T.
Is it negative 3.43?
Alichna.
Little bit.
Yes,
Is it negative 3.43?
no, it's negative 3.4307628888. Did everyone get negative 3.43?
Yeah.
Even better. Did anyone not get negative 3.43 or something approximately equal to that and is not sure why? Does anyone not have a calculator and is not even following along because they can't come prepared to class? You got to bring your calculator to class. Hard to follow if you don't have one. You got it. Need it. Yes.
So, because I'm getting messed up.
Oh, I'm sorry to hear
No,
that.
no, no, not like that.
Oh, okay.
So when do we know when we have to do the sample and then the interval test? Like, what's the difference?
If they say, give me an interval. If they say, do a test. That's how you know. So the test statistic negative 3.43. Part C. Sketch the T distribution and mark the location of the test statistic. It's a very easy way of doing this. Very easy way of doing this. Sketch the relevant T distribution and mark the location of the test statistic. Very easy way. How? No, it's not normal, it's T. Go back to that test you just did. Go back to the test you just did, the two sample T tests,
You go data?
and draw. Don't calculate. Dr-
Yeah, it says there.
If it has an error, it's because
Just drop it?
something else is wrong with your calculator.
So how do we fix that? What about?
You probably have stat plot on, maybe? Bring it here, I'll fix it quick. I know you do.
I drew it, bro.
So you draw, what to draw? Invalid dimension, so let's take a look. See, your stat plot is on, what did I tell you? Because I told you, you gotta fix the stat plot. I literally said, fix the stat plot.
So you turn that off?
Turn that off.
How you turn off stat plot?
Second Y, stat plot's on, hit it, off. Second Y, stat plot. Now it should work.
But I think shows up on the graph. It's taking its time.
Okay, but it's drawing. Stat plot,
Might have to change it back when we take the final.
what the hell is that? No, Steve, stat plot's on. I
Yeah, you
turn it
told
off.
us to Turn it on.
No, I told you, just put it on when you have a problem that requires it, but you don't keep it on. Yeah,
So it looks like that.
yeah. Stat plot is off or on?
It's on, so I want it on.
Oh, no, your stat plot's off.
Oh, it is.
Now, but we go here, now you, 300.4, SX1 was 34.9, and one was 1,000. X2 bar 305.4, SX2 was 30.1, and two was 1,000 not equal, pools. We go to draw. And there it is.
Professor,
What do you want?
dang, never mind.
All your
then.
stat plots are on. Turn all your stopwatches off.
What happened to
Not at
that
all.
nice attitude you had in the morning?
What can I do you for?
We're getting there.
Does it stay like that?
Oh, I went back.
I
How
have
do you go back?
this. Why would it not?
How do you go back on this?
Oh, this makes nonsense. 34.9.
Professor, how do you go back on this, on the calculator?
Hold on.
I don't know what I did.
I
I
don't
hit
know.
enter twice.
Stop pause on, turn stop plot off. Stats, 2 sample t-tests. Go down to draw.
Oh, I don't even.
There we go.
Okay,
Okay.
thank you.
So draw it and mark your test statistic. Where's your test statistic on that graph? No, it's on the left and right.
It's both shaded on the left and the right.
No, that's because it's so close to the x-axis that it looks like it's shaded. Find negative 3.43. Where's that located? On the left. Right? Negative 3. Hello? Negative 3.43 is on the left, correct? Shade in the area representing the p-value. Shade in the area representing the p-value. No. It just looks that way because it's so close to the x-axis. I know, I'm looking at your sketch shaded in. You were told to sketch one. Shade in the area on your graph that corresponds to the p-value. Where would you shade? No, 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 both. Why both? It's a not equal to. So you go to the left of negative 3.43 and you shade it all. But you also shade the corresponding part on the far right side of the graph, yes?
Would it shade it for me or not?
It might. Maybe that's what it means. Maybe that's why it's so thick. Hold on, I'm gonna zoom. I'm gonna do a zoom box. 1 second. Hold on, I'm gonna try. I'm gonna do a zoom box and see. What? Maybe it's shaded, I can't tell. Either way, you would shade both parts. You don't, you do it on your sketch. I said sketch it. That's what a sketch is.
Yeah, but all it's like legit, like close to the x-axis.
Yes, it's legit that way, yes.
What am I sketching?
Just you're shading in the far left and the far right. What?
What is it? Negative 3.4.
That means you're 3.5 standard deviations below the mean.
Why don't you say, why don't you just use standard deviation?
So, part D, compute the p-value. What's the p-value? What's the p-value?
0.
0. Go back to your calculator and have it compute the p-value for you. Yes?
Why don't you use standard deviation?
I don't know, man. I'll bring it up at the next statistics meeting. Yes,
0.000614.
I think it missed a 0. 5 zeros. No, 3 zeros. 3 zeros. Sorry, 3 zeros. Sorry, 3 zeros. And then finally, what is your conclusion?
Reject, try to reject.
Why? It's less than 5%. If the p-value is low, the null must vamoose. I'm a poet. I didn't even realize it. You know my favorite poem? Roses are red, violets are blue. Most poems rhyme, but this one doesn't.
Oh, you know what mine is? Roses are red. Actually, I can't say what.
Say it, go for it. Hold on, let me turn this thing off. Before you do something really stupid. Hold on. Emma, you're back. That's good.